Okay guys, so now we're going to discuss electrical circuits and how to draw circuit diagrams. Okay, so it says here, the circuitry of the simple diagram is much easier to represent using schematic diagrams. So as you can see to the right here, we have this diagram right here. This is a diagram of an electrical circuit. We're going to see on the next slide different components of a circuit. So you'll see here there's a switch, an energy source, conducting wires, and a light bulb. But it's much more difficult to draw a diagram with these pictures. So there's something called a schematic diagram. And this is a representation of an electrical circuit using different symbols for each of the components. So you'll see here, this is the symbol for a light bulb. This is the symbol for a 2-cell battery. This is the symbol for an open switch. Much more simple than this diagram up here where you actually have the pictures. So we're going to learn how to draw these schematic diagrams, and it's very important to use a pencil and a ruler when drawing these. Okay, so very important components of a circuit. So every circuit must have these 4 main components. So number 1 is the energy source. So in this case, the battery here represents the energy source. This actually happens to be specifically a 2-cell energy source. A battery is made up of 2 or more cells. So this is representative of the positive terminal or the cathode. This is representative of the negative terminal. So the smaller line is always the negative and the longer line is always the positive. So guys, an energy source provides energy for electricity to travel through the circuit. So it provides that energy to get the electrons moving. So some examples of an energy source would be a battery or an electric cell or an outlet. Okay, that's going to provide the circuit with electricity in order for electrons to be able to flow. Secondly, here we have a load. Oops. Okay, a load. And in this diagram, this light bulb is representative of the load. Now, a load is a device that the circuit is designed to power. So in this case, this circuit is designed to power and to provide electricity so that the light bulb works. So the light bulb would be the example of the load. Other examples of loads, guys, would be like a TV, a clock. So again, the device that the circuit is designed to power. Next, we have control device. Okay, so a control device in this diagram is representative of the switch. Okay, this switch, more specifically, is an open switch, which we'll see more when we look at our symbols for circuit diagrams. And a switch is the device used to open and close the circuit. So a switch, when it's open, that means that there's no power to the circuit, which means electrons, we've seen this in our past lessons, electrons are going to flow out of the negative terminal, okay, and then they're going to come back to the positive terminal. Okay, but if the switch is open, okay, that almost means like there's a break in the circuit, which means that the electrons aren't going to flow because they aren't able to travel all the way around the circuit. So this is an example of an open switch where the power would be off. A switch that is closed is going to provide power to the load, so in this case, the light bulb. Okay, and lastly, sorry, I just want to make this better. And lastly, we have the conducting wires. Okay, so the conducting wires are what transfer the energy. So these conducting wires are the conductors. So we know metals are good conductors, and they are going to allow electricity to flow. The electrons are going to travel through the conducting wires to transfer the energy around the circuit. Okay, so 4 components of a circuit: an energy source, example would be battery; a load, example would be a light bulb; a control device, which an example would be a switch, or specifically like a light switch in your bedroom; and then number 4, conducting wires. So the conductor, like copper wires. Okay, so we're going to learn how to draw these circuit diagrams, but in order to draw these circuit diagrams, we need to know the symbols for the different components of a circuit. So we're going to go through each one. So this here is the symbol for an electrical cell. So this is just for one cell. So if a question says draw one cell, then you're going to have a positive and a negative. Okay, so I'm just going to redraw this. A cell can also be drawn in the opposite way. So positive, negative. Okay. Okay, so it can be rotated. It can be drawn the other way as well. Okay, so that's the symbol for an electrical cell. A longer line and a shorter line. The longer line represents the positive end or terminal, and the shorter line represents the negative. So that's representative of one electrical cell. A battery is made up of 2 or more cells. So 2 cells would be considered a battery. So in this case, it's just drawn double. So there's 2 of them. So if we look up here, there was 1 cell. Now there's 2 cells. So we have so we have 1, 2. Okay, positive is the longer, negative is the shorter. Now you could also flip this and draw it the other way in a circuit as well. So this is correct as well. Big, little, little. Those are the connecting wires, positive, negative terminal. Okay, control devices. So this is representative, guys, of a open switch. Okay, that's when there's no power. Open switch. Okay, so that's going to be no power. This is a closed switch where electrons are able to travel all the way around the circuit from the negative to the positive terminal. Okay, if the switch is closed, then the load, so the light bulb, will be lit. This is the symbol for a fuse. Okay, so that was switch. Here's the symbol for a fuse. And again, depending on where it's put in the circuit, it can be flipped and drawn like this. As well. Okay, so when measuring current, we're going to learn that we use an ammeter. This is a device to measure current. And when measuring voltage, we use a voltmeter. So an ammeter symbol looks like this, an A inside the circle, and it's drawn directly in the circuit. And then the voltmeter looks like this, a V inside a circuit, and then this is added across the circuit. So it's not attached right into the circuit, but it's kind of added on the outside of the energy source. Then for our loads, there are different loads that can be drawn in a schematic circuit. So a light bulb, a motor, a clock. Okay, so these are all the symbols: a light bulb, motor, clock. Okay, motor and clock is just an M and a C inside a circle. Okay, and then the light bulb does not need to be that perfect. Okay, but anything that looks, say, something like that is good for a light bulb. And then TV is not drawn here, but TV is just like the motor and the clock. It's TV written inside a circle, and then those are always representative of the conducting wires. Then we have a resistor here. Okay, so we will talk about what a resistor is in our next lesson, but a resistor adds resistance to a circuit. Okay, so this is a symbol for a resistor, and again, guys, remember it can be flipped depending on how it's added. So this, that wasn't perfect, but you could flip it and draw it in like that as well. And then lastly, conducting wires is just the straight lines around the circuit. Okay, those straight lines are representing conductor. Okay, so these are all the symbols that are going to be used in these circuit diagrams when we go and draw them. Okay, so now we're going to talk a little bit about what current and voltage is. So it says here, current is the movement of charges. So count the number of electrons. So we're going to use an analogy here. So think of the electrons as cars driving that pass through a certain cross-sectional area of the wire. So we're thinking about electrons moving across a conducting wire, moving through a conducting wire. The electrons being represented as the cars, and the passing through the wire being representative of a toll booth. Okay, so cars passing a toll booth. And divide that number by the time it took for those charges, okay, so again, the electrons are the cars, so that's charges, to pass. Okay, so the flow of electrons, or the flow of electricity through the conductor or the conducting wires. This is what powers household appliances. Very important, you can use an ammeter connected into the circuit to measure current. So an ammeter is a device that measures current, and the unit that current is measured in is amps. Okay, so we have a diagram down here. Okay, current flow analogy. So again, current is the flow of electrons, the movement of charges. So the movement or flow of electrons. And if you look here, we have this diagram where we have a tap with more water coming out, and that represents higher current versus a tap with less water flowing, which is lower current. Okay, so we use this water analogy to say the more water flowing, that's representative of a higher current, right? Because water is representing the charges, so specifically the electrons. The more water flowing, the higher the current, because current is the flow of electrons, and the less water flowing, okay, so the less flow of electrons would be a lower current. Okay, I also have this diagram up here, guys, which we are going to see a couple times. When we talk about current, voltage, and resistance, which we'll get into those terms soon, there is a water tank analogy that's used to kind of compare these different terms and kind of like the relationship between them. So right now we're just going to focus on current, okay? But again, same thing. Over here it says amperage, so that's where we're talking about current. Current is the flow of electrons. So again, in this water tank analogy, we have the tank up here, okay? And then this hose down here that would drain the water out. And when we use this analogy, I want you to remember that water represents the charge, okay? So specifically electrons. And the flow of the water represents current, okay? So the flow of the electrons, the flow of the water is representative of current. The more water, if there's more amount of water, then that's going to increase the flow. If there's less water, that's going to decrease flow. So the more electrons, the higher the current, the less electrons, the lower the current. Okay, so again, using this water analogy to say that water represents the electrons, and the flow of water is representative of current, the flow of electrons. Okay, voltage, also known as potential difference. The difference in the amount of energy per unit charge, the charge being electrons, between two different points in a circuit. So voltage or potential difference describes the difference in the amount of energy between two different points in a circuit. So we can use this delivery truck theory or analogy to describe this. It says the truck delivers boxes, okay, and those boxes, guys, are equal to the number of volts at each load, then refills when gone back through the battery. Okay, so the boxes delivered at each stop is equivalent or equal to the number of volts at each load in a circuit. So the voltage or number of volts at the first light bulb, then the second light bulb, then the motor, and so on. When the delivery truck driver goes back to, say, the warehouse to refill up on packages, that's like representing the number of volts or voltage being refilled or restored when going back to the energy source. So for example, the battery. Okay, so again, the difference in the amount of energy between 2 points. So the difference in energy between, say, the battery and the first load, or the first load and the second load, and so on and so forth. In order to measure voltage, we use a device called a voltmeter connected to a circuit, and voltage is measured in volts. So that's the unit of measurement for voltage. So again, we're going to use this water analogy. So it says over here, more energy equals higher voltage, less energy equals lower voltage. So again, with this water tank analogy, we have the tank up over here, and then the hose connected. And in this analogy, voltage is represented by water pressure. So up in the tank here, we have greater water pressure. So greater voltage, and then down in the hose we have a decrease in water pressure, so a decrease in voltage. So this represents how there can be a difference in the amount of energy from one point to another in a circuit. Okay, and it's important to note that as voltage or water pressure increases, so does the flow of water. Okay, so that's to compare that when voltage increases, so does current, okay? Or down in the hose, when water pressure decreases, so when voltage decreases, that also decreases the amount of water flowing. So current, which is the flow of electricity or the flow of electrons, would decrease as well. Okay, so now we're going to talk about series circuits. So we're going to talk about two different circuits, series and parallel. In a series circuit, electrons can only follow one path. Okay, electrons can only follow one path. That's very important. There's only one path for the electrons to flow through. Loads are connected one after another in a continuous loop. Okay, loads are connected one after another in a continuous loop. An example of this would be old-style Christmas lights. Okay, so what that means is they used to make Christmas lights wired in series circuits. Okay, so that's why when one light bulb went out, the entire strand of Christmas lights wouldn't work. Okay, so if you look down here in this circuit example, so the electrons are going to flow out of the negative terminal, okay? They're going to follow just one path. Okay, there's only one path to follow. Okay, and then they're going to come back to the positive terminal, right? They're repelled by the negative and attracted to the positive, and you'll see here that there is only one path to follow. So down here, there's not more than one path to follow. Okay, so again, think of it like Christmas lights. If this light bulb here wasn't working, then that means that there would be a break in the circuit and electricity would not be able to flow. So even if just one light bulb of all of them wasn't working, then the entire strand wouldn't work because there's only one path for the electrons to flow through. and again, there would be a break in the circuit. Okay, and remember guys, this diagram down here is the schematic diagram. Schematic diagram of this diagram over here. Okay, remember using symbols instead of the diagrams. Okay, so they're representing the same thing. Okay, now parallel circuits are different because electrons can follow more than one path. Okay, so electrons can follow more than one path. Okay, that's very important. Series, only one path for the electrons to follow. In parallel, there is more than one path. Circuit contains two or more branches. Okay, so electrons can go in different directions. Allow you to turn off one load while keeping other loads on. So this is a type of circuit where one light bulb could be off, but the other light bulb can be on. Example would be new style Christmas lights. So now in the new style Christmas lights, they are wired where there's more than one path for the electrons to flow or for the electricity to flow. So if there's one light bulb out, it might just be a small section of the strand of lights as opposed to the entire strand being out. So if you look down here, same thing, I'm going to show you that there is now more than one path for electrons to flow. So they're going to come out the negative terminal, come up, and they can either go this way or this way. So that's more than one path to follow before coming back to the positive terminal. Okay, so parallel circuits allow for some loads to be off while others are on. Most importantly, more than one path for the electrons to flow. Okay, voltmeters are connected across the component. Okay, not within. So when we go and draw these circuit diagrams, it's important to note that when you're adding a voltmeter, now remember a voltmeter measures the voltage, so we like to put the voltmeter around the energy source so that we can measure the voltage at the, for example, cell or battery. When we draw the voltmeter, or in real life, is connected, it's connected across, so like outside the circuit, it's not added directly into the circuit. Okay, whereas an ammeter is connected directly in a circuit. So we'll see when we draw these. I'm just going to do a quick example. Oh, guys, the slide accidentally changed there, so I'm just going to do the quick example right over here on the side. So I'm going to do a quick example. If you were to draw a circuit, okay, this would be the energy source, positive, negative. Okay, when measuring the voltage, you connect the voltmeter across. So you add it in like this. Okay, whereas when you are connecting an ammeter, you put it right in the circuit. So it would be, if this was the battery, then the ammeter would be added directly inside. Okay? Okay, so we have an example here. It says a series circuit consisting of. So we're going to fill in the blanks here. So we're going to look at the schematic diagram. Okay, we need to remember our symbols and what they mean, and we're going to fill in the missing pieces of information. So it says here, blank volt, 2 cell. So this is talking about the energy source. So we have to go and look at our energy source symbol. So in that case, that's right here. Okay, we know that a battery is made up of 2 cells. Okay, so we have 2 cells here. And it's important to know that 1 cell is equal to 1.5 volts. So a 2-cell battery is going to be double that, 3 volts. Okay, a 3-cell battery, okay, each cell represents 1.5 volts, so every time you're going to add 1.5 volts. So 3 cells would be 4.5 volt. Okay, so we have 2 cells here, so that means it's 1.5 plus 1.5, so we have a 3 volt battery. So we'll write that in. Okay, and then now blank source. So we know that the 3-volt battery is the electrical source or energy source. And then a blank switch. So we have our switch right here. So is this open or closed? In our symbols, we learned that that is an open switch. Okay, blank ohm resistor. So when we talk about resistance in our next lesson, you're going to learn that resistance is measured in ohms. Okay, but at this point, we do know that this is the resistor symbol. So that is going to be 2 ohms. And then we have comma and 3 light bulbs. So we have 3 light bulbs here. Okay, 1 light bulb, 2, 3, which means that we haven't covered this guy, and that is the symbol for a fuse. Okay, so just picking out the symbols here. Okay guys, so we're going to do a couple practice questions where we draw the circuits together. So it says here, create a series circuit below consisting of. So number 1, you have to remember if it says series, you know there's only going to be one path for the electrons to flow. I have the example here already, but I'm going to walk us through how we get there. So we're going to go step by step with the information given. So we have a 3-volt electrical source. So we need to remember that 3 volts is equal to a 2-cell battery or a 2-cell energy source, right? Because one cell is 1.5 volts, so 3 volts is 2 cells. So we're going to draw that here. So 1 cell looks like that, 2 cells look like that. Okay, positive, negative. Positive is the longer line, negative is the shorter line. Okay, then it says 2 light bulbs in series and an open switch. So remember there's only one path, so we just have to draw our connecting wires in like a rectangular form. So we have 2 light bulbs, series, and an open switch. So guys, it doesn't matter where you put the light bulbs. So I'm actually going to put the light bulbs in a different spot in my new drawing here. Okay, so it says an open switch. So I could go like this, decide to do my switch here, and then come down and do both my light bulbs down here. Okay, this is the exact same as this one over here. We have a 2-cell battery, an open switch, and 2 light bulbs in series. There's only one path for the electrons to flow, out the negative, all the way around back to the positive. Okay, a 3-volt electrical source, 2 light bulbs in parallel, and an open switch that controls both the light bulbs. So again, 3 volts, guys, we need to make the connection that means a 2 cells, right? 1 cell is 1.5 volts, 2 cells is 3 volts. So we're going to do 2-cell battery. Okay. It says 2 light bulbs in parallel. So what that means, guys, is that the light bulbs are in separate paths. So when you go and draw this, both light bulbs have to be in a different path on the diagram, and then an open switch that controls both light bulbs. So the switch needs to be positioned in the circuit where the electrons are going to flow through it no matter what. So we're going to draw our switch right away. It's an open switch. So this is actually a mistake. This should look like this, guys. So it's an open switch. And now we have 2 light bulbs in different paths. So that's one path for one light bulb and a second path for another light bulb. Okay, putting the switch here, okay, is going to control both light bulbs because it's not specifically in these 2 separate paths. It comes before those paths. Okay, keep in mind you can also draw a circuit like this, guys. Okay, this isn't wrong. If you were to have done battery like this, and then do switch like this, okay, come up and do one path this way, other path this way. Okay, so it can be flipped the other way, that's fine as well. Okay, next, 4.5 volts electrical source, 2 light bulbs in parallel, and a switch that controls each light bulb separately. So in the last question, we had the switch come right after the battery, so that switch can control both light bulbs, but if we want to control both light bulbs separately, both of those light bulbs each have to have their own switch in their own path. So 4.5 volts, guys, is going to be 3 cells, right? One cell is 1.5 volts, 2 cells is 3 volts, 3 cells is 4.5 volts. Now we want 2 light bulbs in parallel, okay, but each has their own switch, okay? It doesn't specify if it's open or closed here, so we're just going to do closed, then our light bulb for our first path. Then we have another switch to control another light bulb in a second path because it's parallel. Parallel means more than one path to follow. So let's do this last example here. It says a 3-cell battery. So we're going to go 1 cell, 2 cell, 3 cells, positive, negative. Then it says a light and a motor in series. Okay, so those are our loads. It doesn't matter the order, guys. Series means one path. We're going to include a voltmeter to measure the voltage of the cell. So we want to add in our voltmeter across the battery here, an ammeter to measure current, and an open switch. Okay, so it's important to measure the current right after the electrical source. So I'm going to add the ammeter in first. Okay, I'm going to come up. Now I'm going to add my open switch. Okay, and now we need a light and a motor in series. So I'm going to come down, I'm going to do my light here, and do my motor here. It's a circle. Then I'm going to come back to my positive terminal, and now I just need to add in the voltmeter, which we add in across the battery like that. Okay, so we did our 3-cell battery. We have our light and motor in series. We had a voltmeter to measure the voltage of the cell. We added an ammeter to measure the current, and we added an open switch. Okay, so you guys have a little bit of practice on pages 26 to 27 in your booklet. Thanks, guys.